So thank you for giving me the opportunity to speak today. I want to talk about how machine learning strategies can help us with the task of variable source classification, especially in the situation of having very large all-sky astronomical surveys with quite often sparse light curves. So all the approaches I'm talking today are very generic, very general approaches that can be used for almost any kind of astronomical surveys and also for almost any kind of variable or transient sources. And we have applied all of these methods to the PanSTARRS 1.3 survey. To give an idea of how that data can look, I want to first give a very short introduction into the survey. So the PanSTARRS 1.3 survey, in one sentence to summarize it, is an optical and near-infrared astronomical survey, and it's covering about 3/4 of the sky in 5 wavebands, and it is a rather deep survey up to about 23.2 magnitudes. And now comes the problem: it has only about 60 to 70 visits, so observations over about 3.5-year period. So this means it results in a rather sparse light curve, like you see here. So the colors represent our 5 wavebands, and this is here fully 3.5 years. So you see we have only a few data points, and it would be hard to do something like, for example, period finding from this data. Just to say it briefly, in the end we will be able to do period finding from that and to say which kind of source this is. But it is, of course, a big task to carry this out. But it is something that's very interesting, because such a survey enables us to map, for example, the galactic halo out to about 120 kiloparsec. And this means we can cover a lot of our Milky Way. In the next slide here you see an artistic image of our Milky Way. What you see here as a green circle, that's the 10 kiloparsec limit of the SDSS studies for kinematics and metallicity. These studies were only covering parts of the galactic bar, parts of the arms, but only barely the halo or even the outer halo. But there's a lot of stuff going on in the halo, and that's how our Milky Way looks as an artistic image from larger surveys like PS1 or the upcoming LSST. So PS1 enables us to cover all of the galactic bar, about the everything about the spiral arms, the inner halo, and even almost everything of the outer halo within 3/4 of the sky. So this means we can say something about, for example, streams from infalling dwarf galaxies. We can say something about how our galaxy, especially the old halo, has evolved, and so on. So what we have started out in the beginning are not proper light curves, or not object classifications, but we had to really to model a survey, and this means to do everything on our own. For example, carrying out outlier detection. Outliers in our case are data points within a light curve that are simply not correct. Then what we want to do is describing light curve characteristics. These are so-called features that describe, for example, how much a light curve is varying, if there is any sign of periodicity, and so on. Then, after having features available from our own model, we can continue with classifying sources to build up catalogs. And then, when we have catalogs, we can continue with finding substructure, with taking a look at all the interesting stuff going on in a halo. So especially for 2 of these tasks, machine learning is very, very important. We can use, and we have used, machine learning for all 4 tasks, but what we had really started out with was describing the data quality and looking for outliers, and then doing some classification based on light curve features that we got, in our case, without machine learning. All the approaches should be, and are in our case, very generic and very general, as we just don't want to build up a good stack of software and then being not able to use it to another large upcoming survey. For example, LSST is something that we want to target later on. All of the stuff is depending strongly on computational performance, so we have used, of course, any of the or some of the large computing centers available, like for example in Garching, Munich, and so on. This is a very challenging task, but it enables a new generation of doing population studies in the outer halo based on, for example, RRB stars. This is a subclass of RR Lyrae. This means also we have a huge and a homogeneous sample because all of our data come from the same survey. So, as I said, we want to apply machine learning. Machine learning is basically a subfield of computer science that gives computers the ability to learn without explicitly being programmed. This is very important here, as if you remember the Lie curve, it looks very sparse. We would have no idea on how to deal on our own with such kind of Lie curve, and we must enable a computer to make use of what it is knowing about Lie curves and how it can find some rules on how to deal with the sparse Lie curves. There are typically two kinds of machine learning that are interesting. One of them is supervised learning. This means learning to infer a function from labeled training data. For example, this is useful for classification, and this means that based on some specific properties, we call them features, the computer should decide if this is, for example, an RR Lyrae star, it's a quasar, it's a non-varying standard star like our Sun, or it's an asteroid. Then another branch is unsupervised learning. This is some kind of generalization of internal structure in parameter space. Parameter space here can mean something rather abstract, like color, like variability, like position on a photographic plate, on a CCD, whatever. But it could also mean something like position in a three-dimensional space. This kind of machine learning, the unsupervised machine learning, should find out what have certain kind of data in common or not. So the supervised machine learning, with what we started, needs basically a training set. The training set is then given to a classifier. The classifier learns from the training set what are the characteristics of specific categories we are looking for, and then it's applied to a target set, and then each member of the target set gets a probability on how likely it is a member of a certain category. What is very important here is to present to the classifier not only objects that are like what we are looking for example RR Lyrae, but also objects outside our category, for example stars being not RR Lyrae. And what we also need is the same data quality for the training set as for the target set, because otherwise the classifier might learn something that it is not able to apply later on. So what's now interesting is what's going on internally in such a supervised machine learning tool. So what it's made up of is some decision trees. So it's a decision tree based classifier, and the learning process means that binary trees are built up where it's split with respect to a single feature at one time. And the split criteria is made so that features and split points are so selected to produce the smallest impurity in the two resulting nodes based on a training set. Then our classifier is not using only one decision tree, but it's an ensemble method. It means a lot of decision trees are grown from subsets of the training set data. And then, when carrying out the classifying, all these trees are voting for a classification. This means we use all of our trees, classify, and then majority vote is carried out, and that's in the end the random forest classification decision to assign each object we want to classify a probability for being a member of this category. So this approach improves the classification performance a lot because it's less sensitive to training set variances. For example, if you have a bit brighter, a bit shallower sources and so on, if you have a bit better, a bit worse Lie curve, and so on. And it's also quite robust to outliers. If you maybe have not catched some kind of outliers, it can deal with it, and it can be usually parallelized. This is extremely important, as for example in our case we had to deal with 10 to the power of 9 sources, and this cannot be solved without using highly parallelized algorithms. Such kind of classification should be used, of course, never ever without verification. Never ever use it as a black box. So there are several concepts for verification. For example, making use of a training set to carrying out a so-called tenfold cross-validation. This means 10% of our training set are holdout. This shouldn't affect the build-up of the internal structure of the classifier a lot because we have so many training set data. Then the training is carried out on the remaining 90%, and we are applying it to the 10% holdout in turn. And then what we get is something we call a precision recall curve. This means this gives us information about how good our classifier works. You see here many curves. Some are rather rectangular, some are very steep. So just to give an idea on how this works, the ideal curve would look like a rectangle. Usually we cannot get this, but as close as to a rectangle, the better it is. So what we are doing with this kind of classifier is first doing some kind of outlier detection. Photometric outliers can cause some spurious variability, so it looks like there is variability going on, but it is not indeed. Traditional solutions would use flags, for example, blending, off-chip, and so on, or point spread function minus aperture magnitude cuts, so morphology on an object. What we did was applying machine learning, starting out with a bunch of objects where we assume there is no significant variability going on, so for example bright K and G stars. This enables us to find out if there are any outliers based on how the observations were done. Then we can train regarding that and can find out what is causing outliers. This approach is working about 3 times better. This means we can, with our method, we can find about 80% of the outliers, and we have only a misclassification rate of 1. This means 1 misclassified for 1 correct. This is way better than the old solution. An application is, or the most important application here is the variability classification, characterization. So this means we want to classify light curves. We cannot classify directly light curves, but we want to convert the light curves using some kind of signal processing into numbers, into our features. And what's very challenging here is that we have non-simultaneous data. This means, for example, we cannot easily calculate something like colors. Colors are very important in astronomy, but here it is hard when you have, for example, an observation in the G band, and then 2 days later you have one in the R band. How to calculate the G minus R color if you have a varying source? So then, as usual, we have noise, we have uncertainties of our data, we have some foreground effects, and the time sampling, as you have seen in the light curve I had shown in the beginning, is affecting a lot on how light curves look. So we could miss out some characteristic features, we could miss out some periodicity and so on, and quite often because we don't know about the object, we're not knowing what we are missing about. Yeah, periodicity. This is, of course, something very, very important. A lot of interesting astronomical sources are varying at a characteristic period. For example, eclipsing binaries, Lyrae stars, and Cepheids. But yeah, the cadence of the survey, so the time steps at which we are observing, might mask this out. And even not all variable sources are periodic. For example, quasars are varying a lot, but not periodic. So we can apply some methods to detect period, but not the usual methods. There are a lot of usual methods that are also say that work out with some kind of sparse data, but for us, just the data were too sparse. So one is, for example, the Lomskal algorithm, and this kind of light curve you see in the bottom, it's ways better populated than what we are dealing with. So we tried that and we failed immediately. We tried to improve it and failed again and had to bring up something new. What we brought up was template fitting. This works in the following way. We have first to use a survey that has quite a good sampling. This is, for example, SDSS stripe 82. And then we are creating some light curve templates. These are the curves you see in the panel below, just based from this data, and we are trying to fit these kind of templates to our data. What you see below is the data points from a source from pen stars, and the best fit model out of stripe 82 is overlaid. So this looks a bit tricky, but it works very, very good, and we can determine phases down to something like seconds. For our non-periodic variables, and also to give to make some kind of a baseline on how to classify and how to describe varying sources, we have to start out with something different. And yeah, we need this also for pre-selection, because the period finding is computationally very expensive. So we should only apply this to sources that look like having maybe a period. So what we started out is with non-periodic feature extraction, and this is also done with methods we have developed especially for this case, because everything that was available just didn't fit our situation. So what maybe someone of you might know is structure functions. So light curve or any other kind of time series data can be described as a stochastic process. For example, using Gaussian process with parameters can be determined by using a structure function. This is a method from the 90s and was used a lot, for example, for black hole reverberation mapping and other kind of dealing with light curve data. What we have done then is to extend this kind of algorithms to deal with multiband data. Variability in this case is wavelengths depending, also colors cannot easily be determined, and so we brought up the idea of multiband structure functions. Here's a bit of mathematics describing that a structure function is basically something that has to do with our expectation value and how a light curve might look like. And here the alpha is describing the wavelengths depending part of our function. We are then fitting an amplitude and a variability timescale to our data, and get a characteristic variability timescale and amplitude for each object. Here you see two example light curves, and our algorithm is indeed able to find out which of these two light curves are coming from a QSO or from our Lyrae star. This is how the structure function fit looks like, and indeed it properly assigns the first one is an Lyrae star, and can give a timescale. Timescale is not a period, but it is some characteristic property, and it can also properly assign a longer timescale for the QSO. So this is now a big map of our Lyrae stars that we found in our Milky Way. These are more than 50,000 stars distributed over the complete survey volume, and what you see here are some clustering effects, and these are, for example, overdensities like streams. You also might spot some dwarf galaxies and so on. So what we're most interested in is now doing some science with the streams, and here is, for example, Sagittarius stream. You see here a view on a stream. You see the data points we use for fitting, and you see the green points as our fitting result. The movie, please. So what you see right now is our complete data volume, and the color encodes the distance to the center, where the center is not a galactic center, but the position of our sun. And after a while, you will see that some data points fade out, and what's left over is this large outer structure. That's the Sagittarius stream. This is exactly what you had seen in the image in my presentation. So the stream is composed of two large arms, leading and trailing arm, also called leading and trailing tail. What we made, as you see here, is some three-dimensional representation of our data, and we were able to fit for the first time the stream in 3D. So continue with the presentation, please. So to summarize, what we got from this UTF-4 and our PS1 3Pi data was identification of our Lyrae stars in QSOs that works very well with a high level of purity and completeness, and we were able to carry out the fit for the Sagittarius stream, and we're now developing capabilities for Cepheids. And of course, we had published a lot of results regarding how to build a catalog, how to fit Sagittarius stream, and also how further on the Milky Way halo is shaped, and we're continuing with a lot more. We started a spectroscopic survey regarding special targets, and so on. So in the end, my take-home message is that with the right algorithms at hand, even sparse data, sparse light curves can lead to surprisingly good classification. Thank you.
Thank you very much. Anyone have a question? I don't know where the box is anymore, actually.
There.
Any questions? Koen? That's a challenge, right?
Yeah.
I think you woke up some people.
So my impression was that the RR Lyrae that you fit, you were actually in the end doing template fitting and not machine learning.
No. The template fitting results into some features, and we are using machine learning in a 8-dimensional space with random forest classifier. So the template fitting gives us only an idea about if this shape of light curve fits about to an RR Lyrae and what is the period. We're doing this for the training set, and we're doing this for the target set, and then machine learning is going on. So I wanted to focus here more on the feature extraction because this is especially very complicated with sparse data.
Can I ask a thought? So supposing you had only done template fitting, do you think you would have missed many RR Lyrae?
With only template fitting, we might have not missed many, but the computational effort would have been just way too much, because then we had to start out with template fitting on about 10 to the 9 sources instead of, in our case, 100,000. This is not feasible. And also in the end, we would have ended up with how good a template fit, but not with an idea if this is an RR Lyrae. For example, we can, from our structure function, also estimate the colors, even in the case of having sparse and irregular data. Yeah.
Your misclassification rate that you mentioned as 1, that is 1 correct and 1 wrong,
yes, this is for outliers. So this means we find some outliers, of course, and let's say when our code says it detects 2 outliers, then one of them is an outlier and one would have been not. But with a traditional method, when we detect 4 outliers, one is a true one and 3 data points are lost for nothing because they would have not been an outlier.
But how do you determine what is the correct outlier and what is not a correct outlier? Because that's one of the trickiest questions.
We are determining this from our training set data during validation, and we're determining this from K and G stars, where we assume there is no or not much variability going on, because many of the Lyrae stars and also other sources within the PS1 3Pi survey are observed for